Welcome back to CST432 Microprocessors and Embedded Systems. Today we will continue our part 2 of Decisions. The topics we will be covering in this module today is how do we make decisions using lookup tables. And then we will apply it towards the mover robot and how we can implement a robot system using lookup tables. When we talk about decision making, we have to take into consideration two different aspects. The first type of decision making involves high-level decision making, which examples of which are like goal seeking, objective optimization, and various heuristic-based approaches for reaching a certain objective. Now, low-level decision making is what we are going to focus on in this module. This involves short-term goals, such as line following, which we have looked at previously. In addition, decision making often involves choosing among multiple finite options. And typically, when we are doing programming, this involves the use of if, then, and else constructs, or else the switch case construct found in the C language. Switch statements allow us to make multiple choice decisions. Basically, we will implement this as a jump table where the routine to be called from the switch statement has identical inputs or do not require any inputs at all. So given a line type of either an outside of the line, edge of the line, or inside the line itself, we will decide whether we should move forward, turn clockwise or counterclockwise. And all these can be implemented using a switch statement. Here we will look at how we implement this switch statement as a jump table. First of all, we look at the data declaration section. Here we will define the various routines to be called as entries in an array of routine address pointers. And this array will be ordered in the sequence based on the index value of the switch variable. So given this index value, we will then be able to look up the table to determine the appropriate routine to be called. So when we're given the line type variable, we will call the jump table dispatch algorithm or the line type dispatch routine here to determine the appropriate routine to be dispatched. So first of all, we will compare the input value of the line type against the maximum value available to us to prevent us from calling an unknown or illegal entry in the jump table. First of all, we will compare against the highest index value, and if it is above the highest index value, we will replace it with the default index entry. Next, we will convert the index into an actual address, which is the item address into the jump table array. And given the address of the jump table array entry, we will then load the target routine address into the register for us to be able to call it later. Since we are not calling the routine directly using a branch and link instruction, we must set up the link register manually ourselves. The way to do this in ARM instructions is to use the move lr, PC instruction to copy the program counter value, which currently points to two instructions beyond the current instruction being executed, which is located at the done execution label. This is copied into the link register, after which we will then replace the program counter value with the address of the target instruction target routine to be executed. And by doing the move PC R2, which contains the target instruction address, we will then actually branch to the target routine itself. Now, what if the input value for the jump table selection is coming from a sparse range, meaning that the possible values that the input value can take is quite a large number, but the actual values that will be considered is a limited few out of this range. So to do this effectively, we can use what is called a key lookup technique, where we first perform a key lookup to determine the appropriate index in the jump table to retrieve the actual address of the routine. So example of such a sparse input value technique where it can be used is if we are given, instead of the line type given as an enumerated value of consecutive values starting from 0, we are given instead an ASCII character containing a command to execute. Examples of this are like H to represent halt, S for slow forward, F for fast forward, L for turn left, and R for turn right. Now these input are actually ASCII values that can come from a range of 0 to up to 255. However, you do not wish to store unnecessarily default entries for all the values that are not required for executing an actual action routine. So to avoid this overhead, we will then have a separate key lookup table to store the valid entries that we will execute. Here we have the data definition for the key table. Command char key table is a bite-sized array of the various defined commands. Note that the commands are not sorted as in any order, whether it's ascending or descending. It can be placed in whichever order, but typically if it is a non-sequential list of possible keys, we would sort them based on the most frequently used or most urgent command to the least urgent command. Finally, we terminate the key table with a null entry, which is a value of 0 hex. The actual jump table contains the action routine addresses as normal. However, the sequence in which these are put into the jump table array must follow the sequence used to define the key lookup table itself. If they are out of sequence, the incorrect action routine will be called. Here we will see how we can implement this key lookup jump table. First of all, the input into the routine is the key or command character. The command character will be used to convert into an address pointer for calling the actual routine. Input character that we receive could potentially be uppercase or lowercase. To avoid having to have multiple entries for the same command, we will convert all the possible lowercase values into its equivalent uppercase values using the NR0 with the hash 0xDF hex value. This will convert any lowercase characters found in the input stream into uppercase characters. Subsequent to that, we will then look up the key lookup table to determine whether it is found in the lookup table itself. To determine whether the command is found in the key lookup table, we will do a linear search starting from the beginning of the table until we encounter a null entry. This is similar to the stir-char algorithm that we had looked at previously. If we had managed to find the command in the key lookup table, the index value would have been found in R1. Using the same index value, we would then index into the jump table to determine the appropriate item address for the action routine to be executed. Once we retrieve the action routine address from memory, we will then execute it as similar to the previous approach, where we load the address pointer into a register, then perform the move LRPC sequence followed by the move PC with the register value to transfer control to the subroutine, and upon return we will come back to the done execution label address. Now let's see how we can extend this to even more advanced jump tables. Jump tables can also be used when disjoint range of values are used to trigger an action. So for example, a line classifier dispatcher for the tribot would possibly be able to determine the type of line based on the light sensor input value, whether it is inside, edge or outside, and then and automatically dispatch the corresponding action routine all in one subroutine. To implement this advanced jump table, let's look at the data structure definitions again. Here we have to define the minimum level that would trigger a particular line classification, as well as the maximum level for that line classification, and corresponding to that, the action routine that will be called. Now, the minimum level and maximum level are both byte-sized values. However, the action routine address is a word-sized value. Consequently, 2 bytes of padding will be added to each entry in this jump table. Here we see the actual advanced jump table classification entries. We start with the outside definition, the edge definition, followed by the inside definition or the line definition, and finally we have a default or a catch-all definition which is used to deal with the case of unknown or unrecognized input values. Here we look at the implementation of a generic advanced jump table dispatcher. This dispatcher can be used for more than one type of application as long as it matches the requirement where we have a minimum and maximum range as well as an action routine associated with that classification. So here on input to the routine, we have the minimum value, maximum value, as well as the jump table item pointer and the jump table end pointer for us to determine when we reach the end of the jump table. First, we will keep the jump table beginning and end pointers in R4 and R5 for use later. We next enter the search loop where we will start by checking whether we have reached the end of the jump table entries. If we still haven't finished processing the valid inputs yet, then we will load the target minimum and maximum bounds from the jump table into R2 and R3. Next, we check that the input values are within the minimum and maximum bounds that is defined. If they exceed the bounds or do not fall into the bounds, then we will skip to the next possible entry. To skip to the next entry, we increment the address pointer R4 with the size of the advanced jump table entry, and that will point us to the next valid entry in the table, and then we can resume the loop for the next entry. However, if there is a match, we would retrieve the action routine address from the jump table and then perform the move LRPC and move PC, R0 sequence to call the subroutine and execute the action. Once we are done, we perform any cleanup actions necessary and return the status to the calling routine. Now let's look at how we can apply all these techniques to the mover robot. The objective of mover is to implement all the Grasper behaviors we have studied previously, which is to detect an object by following a line until an object is touched by the touch sensor. And upon the detection of this object, the claws will close around the object, and at this point the mover behavior will take over, where it will listen for sound input, possibly given by a person speaking or shouting or clapping. Now once this sound has been detected, it will then attempt to move towards the source of the sound. Here we have the behavior diagram for mover. We see the addition of the sound input sensor, and with the move object behavior obviously has to be added. Now we have split up the arbiter from being a monolithic arbiter into separate arbiters that are specific to the actuators or controllers that we will be using. So we have three different controllers or arbiters. Grasper arbiter for controlling the claw, the tone generator arbiter for controlling the speaker for sound output, and finally the movement arbiter for controlling the robot motors for the wheels. The mover controller outputs are similar to that for Grasper, except that we have added the move object behavior. In the move object behavior, the claw controller closes the claws, and the motor controller will perform a sound seeking behavior to attempt to move towards the source of the sound. In addition, we have added a column for the speaker, which involves the generation of tones when the robot is idle. In all the other states, it is silent. Here we see the behavior activation triggers for mover. The main difference is in the move object behavior, where if the touch is active and the claws are closed, then it will activate the behavior. At the same time, it will listen for input from the sound sensor, so that if there's any sound received, it would then go through the move object behavior processing sequence. Previously, we talked about how subsumption can be used to implement a more advanced robotic software framework. So to support this using staggered processing, we would assume that behaviors are always active and execute in parallel. And outputs of behaviors are subject to arbitration, meaning that all behaviors are potentially active at any given time. It's only that once the outputs are generated by each behavior, then arbitration occurs. So in order to achieve this in the robotic framework, we need to separate the behavior activation and the arbitration into two separate steps. The first is the dispatcher module to call each behavior in turn so that they can generate the appropriate outputs. And secondly, the arbiter module, which will then decide among the available outputs which are the actual outputs to be sent to the controllers. This is implemented as the NXOS Enhanced Robotic Framework, or known as NERF. So in NERF, we have just added a new module, which is the BBR dispatcher module, highlighted here in this flowchart. So it's only after that all behaviors have been dispatched that the arbiter will kick in and perform arbitration on the outputs. So it is potentially possible that a behavior can have outputs that are passed to the controller for some of the controls, but not for all of them. So you could have multiple behaviors that are concurrently active. Now we look at how we can represent suppression and inhibition in our framework. Remember that we are assuming that we have a fixed priority hierarchical arbitration scheme. So in such a scheme, the suppression will be enforced by arbiter, meaning that the higher priority behavior will suppress any lower priority behavior outputs. In terms of inhibition, in NERF, it is only self-inhibition that will be considered. Self-inhibition, it means that a behavior can only inhibit its own outputs. It does not affect the outputs of other behaviors in terms of inhibition operation. So if an output is inhibited, if the behavior has no interest in them. And special values will be used for indicating such inhibited outputs. Previously, when we were implementing Grasper, we were performing the sensor readings for each sensor sequentially. But bear in mind that sensor readings for a given sensor need to have a 3-minute interval between each read. However, now we have different sensors in operation. The light sensor and the sound sensor are both being accessed for inputs. So in order to avoid duplicating or doubling the sensor delay for each sensor, we can interleave the reading of different sensors such that the total time needed will approximately be 3 times n, where n is the number of input values, milliseconds for n samples, regardless of the number of sensors that are used. We will use the jump table technique to implement the mover dispatcher. This is because each behavior routine will be stored in the jump table and the dispatcher will dispatch each of them in turn. So there is no need for us to perform any checking on the individual routines. For the arbiter, however, we will evaluate the actuator outputs for each controller independently, meaning that we will look at the outputs for the tone generation or the speaker controller separately from the outputs for the claw as well as outputs for the motor. Now we will start with the highest priority behavior actuator outputs for the given controller, for example the claw controller. If the outputs are inhibited, then we will examine the next lower priority output until a non-inhibited output is found. Of course, the lowest priority behavior actuator outputs given by the idle behavior are always enabled, so we will always have a valid output in the end. Once we determine the active controller outputs, we would then need to update the controller by programming the actuators. Now, we would like to minimize the controller updates by first comparing the new actuator state values against the previous actuator state values. Only if there's a change that we would then go ahead and program the individual controllers directly. If there are no differences, we can skip that step and go on to the next module. Now we shall look at how we can re-implement the follow line behavior using lookup table techniques. Previously, the follow line behavior was implemented as a set of specific action routines that perform certain programming to the actuator state output structure. Now in this case, we will use the line classification, perform the line classification using the advanced jump table technique to determine the appropriate action for each line type. And once we know the action routine address, we will then call it to perform the action. But instead of programming the actuator outputs individually, we would store the predefined actuator outputs in a data structure such that For a given line type, all we need to do is to copy the output values using the memMove routine from the predefined output data structure to the target output structure itself. This avoids having to perform different computation for each type of line. Next, we shall look into how we can implement the move object behavior. The move object behavior implements a sound seeking algorithm in order to try and attempt to locate the source of the sound. First, we will have a sound level classifier to determine whether the sound is soft, moderate, or loud. Next, we will take the sound input and put it into a leaky accumulator. We will learn more about what it does later. Based on this output value, we will then perform a state transition using hysteresis control. Again, there are terms that we will define afterwards. And using the state output generated by the state transition, we will then operate action routines that control the actual behavior outputs. This is a conceptual diagram for the move object behavior. First, the sound sensor generates input values. As seen on the diagram, the input values may be intermittent or a long duration. Intermittent input values may be caused by, for example, clapping or a short burst of sound. The long duration of sound may be caused by somebody saying something continuously. So the sound detection is not a steady state detection. Consequently, we must determine and classify the type of sound based on the intensity. This is because if the tripod is facing the source of the sound, the intensity is expected to be higher than if the tripod is facing away from the source of the sound. So in order to try to move towards the sound, source of the sound, we must first of all determine whether we are facing the source of the sound itself. This is implemented using the sound level classifier, which classifies the sound level into quiet, soft, and loud sounds. Once we have the level of the sound classified, we can then increment the leaky accumulator to determine whether we should trigger a certain action or not. The leaky accumulator is basically similar to a bucket with a hole in it. So as we fill the bucket with water, the level of water will rise. However, there is a hole, so things will start leaking out, or water will start leaking out until such time if there's no new water being poured into the bucket, eventually it will drain the bucket and be empty. So this allows us to have a non-standard or non-continuous sound input trigger actions by filling up the bucket up to a certain level before we decide whether a certain action should be done. For example, when we first start doing the move object behavior, the tripod is waiting for something to trigger its action. So the bucket is empty. As somebody starts clapping or shouting or saying something, the detection of the sound will then trigger the tripod to start waiting for enough sound input for it to start seeking for the actual source of the sound. The seeking action triggers the wheels of the tripod to turn and attempt to locate a loud enough volume so that it would then start moving forward. And finally, the following action will be performed once there is enough sound input to ensure that the bucket remains full above a certain threshold. Now we see that the state transition here is implemented using hysteresis, meaning that the level used to trigger the change in the state from a lower state to a higher state is actually needs a higher threshold than compared to the state transition downwards, meaning from a higher state down to a lower state. This is to avoid having continuous toggling between states if the value of the accumulator is at a threshold between two different states. Finally, once we determine the action to be done, whether it is idle, waiting, seeking, or following, we will then generate the appropriate behavior outputs to affect the motors of the wheels, whether to stop, to turn, or to move forward. So to repeat what I have said earlier, some of the details that we need to take into consideration. First of all, the sound sensor input can be intermittent. For example, if you're doing clapping, the sound is not continuous. And secondly, it can be non-regular in intensity, meaning the loudness may vary from one sample to another sample. So secondly, when we're doing sound level classification, we will need to determine the quanta or increment or decrement for the leaky accumulator. If we increment the quanta too quickly, it will change state very rapidly and move from just idle to following in a quick transition. This may or may not be desirable. Similarly, once we are following, we may continue moving despite the absence of sound. For example, this person may have stopped making sound and then the robot still keeps moving because the quanta for decrementing is too small. Again, we need to be careful of how long to keep the state active once there's an absence of input. So the leaky accumulator we use to trigger actions, and the state transitions are based on the leaky accumulator values, but we will use hysteresis to reduce the rapid state transitions. If there is intermittent inputs especially, we would not want it to move from one state to another state very rapidly, but instead have a more orderly transition. By using a lower threshold to exit a state, it will allow us to stay in the state for a while longer. So these are the various software modules for Mover. We have the helper routines, which include the min-max routine we studied previously, the memcomp routine for comparing two different blocks of memory, namely the actuator output values, to determine whether there's any new values that need to be programmed into the actuator. Then of course there's the jump table dispatch routine, which is used to execute the various dispatch the various behaviors. Then the system housekeeping routines remain pretty much the same. Common robot operation routines are also similar, unchanged. And finally, the behavior-based robotics framework has the addition of the dispatcher module and the arbiter module has been modified, as well as the controller module has been split up into the independent individual controllers for each actuator. Finally, the worker routines, some new worker routines have been added to deal with the sound input, as well as various algorithms used for implementing the move object behavior. This is Mover. You will follow the line and detect the object and then grasp it, and after which you will try to track the source of sound and move towards it. Okay, so at this point it's actually waiting for detection of the sound level to exceed a certain threshold before it starts implementing the mover operation. I'm going to sing to it. So after I stop speaking, it will start to try and search for the source of sound again by turning around. But if there's no source of sound, it will stop and be idle. The idle tone you hear here is the idle of behavior triggering. Okay, stop. As usual, these references would be helpful if you would like to find out more information about behavior-based robotics or the ARM instruction set that has been used. Instead of presenting the code directly on this video, I refer you to the actual source code in the URLs listed here. The reason being that the source code is actually quite extended and we cannot discuss each line in detail. If you have any more questions, feel free to talk to me. In any case, I'll see you next time.